We are group E22, and let's start off with a fun fact. Well, not so fun. Did you know that 72% of firefighter on-duty deaths were due to occupational cancer in 2023? Additionally, the average lifespan of a firefighter in the US is approximately only 52 years. That's about 25 years under the national average. Now you can see on this slide a few different types of cancer. And on the left is how much the chances of a firefighter getting them are multiplied compared to a regular person. Now you can see these numbers range from 1.15 to even 2 times as likely compared to the regular person. Now one type of cancer you don't see on this list is lung cancer. There is a 60% increase in lung cancer for firefighters. And this is because they breathe in carcinogens and forever chemicals into their lungs. But you may be asking, don't firefighters have PPE to protect them from this sort of thing? Now, this is a real quote that we got from a firefighter that we interviewed. Now, according to him, their masks are uncomfortable, they're really no better than the N95s that we used during COVID, and they cost a lot. In terms of comfort, this is usually because they all use this one-size-fits-all mask with a rubber exterior. So therefore, because everybody's face is a different shape, it'll press on certain parts of the face and cause abrasions. Now, like I mentioned earlier, a lot of the masks that firefighters use are really no better than N95 in terms of how much they filter. Additionally, they can also cost up to $1,500. So we want to create a solution that is cheaper, more comfortable, and it is better than an N95 in terms of filtration. So let me present to you Smokescreen.
The solution we are currently looking at is a 3D printed mask to take care of the two major issues, cost and comfort. 3D printing allows for the production of a mask at just a few dollars, along with the fact that we are trying to implement quick swappable filters that we can screw on and off, so when the filter is used up or completely full, we can remove just the filter instead of having to replace the full mask, which increases cost effectiveness. We can iterate on comfort with the way we design it, how we can attach to the head, the material coming in contact with the skin, the weight that we use with the amount of filament we use, as well as using heat-resistant filament, etc. Putting all of these together will allow us to solve the problem of the filters on current, cheaper masks being inadequate, while also solving the irritation, the weight, and the cost of larger, more robust glass, metal, mechanical masks that you might see more commonly.
But before we started design, we've had to make some risky assumptions. And these assumptions include heat resistance, the fact that the mask would be able to sustain the temperature in which the firefighters operated in. The mask would also need to be not permeable to the extent that the PFAS would not get through the hard cover. And we also want to make sure that the filters were effective and that the overall mask was cheap and it was also comfortable. And so with our experiments, we have been evaluating these riskiest assumptions, and we will continue doing so in the next couple of weeks.
As Baldwin mentioned, one of our riskiest assumptions was that it was possible to create a mask which is more effective than the current technologies in its ability to filter out toxins. The most popularly used N95 and P100 masks are graded to filter out particulate matter, but not necessarily gaseous toxins, which are known to be toxic and carcinogenic. In a report done by the Department of Homeland Security on the market, currently there exists no commercially available solutions which are able to filter out carbon monoxide. And thus the question is, can we design an effective solution for carbon monoxide exposure in wildland firefighters? And thus we run an experiment using a grand canonical Monte Carlo simulation. We considered two scenarios. One in which carbon monoxide, which is known to be notoriously difficult to capture, is in a box with just the unary species. The other in which it is a unary species in the framework of CuBTC, one of the most studied nanoporous materials. In the box, we found that the density of carbon monoxide was roughly 1.3 kilograms per meters cubed, the same as you would see in the air around us at 1 atmosphere. But within the metal organic framework, it was 445 kilograms per meters cubed, which shows that it is indeed possible to filter out carbon monoxide in a filter.
One test we did was the 3D scanning test, where we tested a bunch of different 3D scanning apps to see if we get a 3D model with the level of detail needed to customize the firefighter masks to fit the face better. And so we tested a bunch of different ones, and we ended up landing on one called 3D Scanner app, which uses the face recognition from they use to unlock their phone. We take a video using that, and it creates a 3D model with enough detail, and that can be exported as a 3D file to customize the mask. The next test we did was the fit test, where we took the 3D mask and we made a prototype and we tried it on to see how comfortable it was. And while it fit the face very well, the hard plastic on the skin was uncomfortable. So we're going to need to redesign this part of the mask so that it meets our standards and that it's more comfortable on the face. This may involve figuring out a different way to seal the mask, but overall, we need to iterate in this area.